Hi, everyone. In today's lesson, we're going to talk about a concept called the mean value theorem. So let's start with the definition. If f of x is a continuous function on the closed interval from a to b and differentiable on the open interval from a to b, then there exists a c in the open interval from a to b such that the instantaneous rate of change at c is equal to the average rate of change over the interval. So that's a lot of words. Let's just break it down a little bit. So basically, the picture I think will really help. So here's your curve, the red piece from A to B, and I'm telling you with the mean value theorem that there is a point in the interval from A to B, which we'll call C, such that the instantaneous rate of change, and remember, instantaneous rate of change means derivative or slope of the tangent line. So there's a point where the derivative or slope of the tangent line is equal to the average rate of change. And remember, average rate of change is simply the slope between 2 points. So let's see if this works. We have some point, which we'll call C, I'll highlight here in red, where the instantaneous rate of change, or the slope of the tangent line, is equal to the slope of the line between 2 points A and B. We call that a secant line when it hits a spot function in 2 spots. So do you see here that these two slopes are equal, right? Parallel lines have the same slope. So really, in symbolic form, the instantaneous rate of change at C is f prime of C. That's the instantaneous rate of change at x equals C, and that's equal to the slope or average rate of change, right? So maybe I'll just get rid of the slope there. Let's just call it average rate of change. So the instantaneous rate of change at C is equal to the average rate of change over that interval. And this is the formula for average rate of change. This is your slope formula. So we're going to be using this formula for the mean value theorem. We're going to set the average rate of change equal to the instantaneous rate of change, and we're going to be able to use it to find this value of C. So let's use an example. Example number 1 says, given the function f of x equals this, what is the average rate of change over the interval from 2 to 6? So average rate of change is slope. So change in y over change in x. And we're going to use, instead of the y values as y2 and y1, we're going to use function notation. So since this is your interval from a to b, we're going to say f of 6, that's your y value, minus f of 2, all over the x values, which are 6 minus 2. So in order to find f of 6, we need to take our function and plug 6 into it. So f of 6, so negative 6 squared plus 3 times 6 plus 10. So just trust my math that f of 6 is equal to negative 8. Now, same thing, if I plugged in 2 into my original function, trust my math again on this one, that when x is equal to 2, y is equal to 12. And we're going to just plug in f of 6 is negative 8 minus 12 over 6 minus 2. Negative 8 minus 12 is negative 20 over 4, which gives me an average rate of change of negative 5. So in part B, I'm asking you to tell me, when is the instantaneous rate of change? When is that equal to the average rate of change? So instantaneous rate of change means derivative, so we need to find that. So I'm going to start with this function up here, f of x, and I'm going to take the derivative. So f prime of x is a simple power rule, negative 2x plus 3. And I want to set that equal to the average rate of change, which I found in part A to be negative 5. So when are these equal? Negative 2x plus 3 equals negative 5. A simple solve here will do. So negative 2x minus 8, divide by negative 2, x is equal to a positive 4. So when x is 4, the instantaneous rate of change and the average rate of change are equal. So if this was a graph, the slope of the tangent line would equal the slope of the secant line. So if you want just a little bit of a visual, you can draw a little bit of a sketch here. So the parabola would look something like this, right? It would be a sad parabola or concave down. And we're looking to see where at x equals 4, so this here crosses at 5, so this would be x equals 4. So at x equals 4, the slope of this tangent line here at x equals 4 is going to be equal to the average rate of change from the curve from 2 to 6. So let's just say this is 2, and over here might be 6. So 2 to 6, this slope would be equal to this slope. Now the picture is not great. Obviously, if you had it graphed, it would be easier to see, but you're really looking to see something like this. The slope of the secant line is equal to the slope of the tangent line. Okay, let's go to the back. So the mean value theorem versus the intermediate value theorem. So the mean value theorem states that the derivative, or the instantaneous rate of change, must equal the average rate of change somewhere on an interval. And the intermediate value theorem tells us that on a given interval, you will have a y value at each of the endpoints of the interval, and every y value exists in between those y values at least once. So let's do an example, maybe where we're going to put all of this together. So we have a hot air balloon is launched into the air with a human pilot. The twice differentiable function h models the balloon's height measured in feet at time t measured in minutes. The table above gives the values of h of t of the balloon at a selected time t. So part A, for the interval from 5 to 15, must there be a time t when the balloon is 50 feet in the air? So they're asking for a y value, right? 50 feet in the air is h of t. So they want to know, is there a y value? So that is the intermediate value theorem. So remember, we need to know where I am at the endpoints of the interval. So I need h of 5 and I need h of 15. So all we're going to do is look at the table. When x is 5, y is 40. When x is 15, y is 70. So will there be a y value of 50 between 40 and 70? The answer is yes. So you would say yes, according to the IVT, there exists a C in 5 less than or equal to t less than or equal to 15, such that h of c equals 50 is in between. You can just say is in the smaller value first, so h of 5 less than or equal to h of c less than or equal to h of 15. Okay, so part B. For time being from 20 to 30, must there be a time t when the balloon's velocity is 1.5 feet per minute? So now that we're talking about velocity, remember the function here, h, models their height. So we need to take a page out of the book from last unit. We know that if we have height or standard position, the velocity is the first derivative. So they're looking for a velocity or the derivative to be 1.5. So this is your intermediate value theorem, your mean value theorem. So you have from 20 to 30. We can find the average rate of change there because remember, our mean value theorem says that the average rate of change must equal the instantaneous rate of change. So first, let's find the average rate of change between 20 and 30. So we have here between 20 and 30, these are my y values and these are my x values. So we're going to do 80 minus 65 over 30 minus 20. So we have 15 over 10, which is 1.5. So my average rate of change is equal to 1.5, and Is there going to be a time when the velocity is equal to 1.5? Yes, because in order for the mean value theorem to work, the average rate of change has to equal the instantaneous rate of change, and velocity is derivative. Derivative means instantaneous rate of change. So if my average rate of change equals 15, then my derivative will have to equal that. So you could just say yes, according to the mean value theorem. There exists an instantaneous rate of change that will equal 1.5. And that's it. Okay, so your homework for tonight is going to be to try example number 3 and come in with that for class tomorrow, and we will start there. Okay, have a good night.